All right, welcome back. And this video is going to cover the last section in Unit 4, which is Section 3.7 over inverses of functions. And we are going to discuss some previously discussed topics involving functions and then add in some additional information. So, first thing, definition of an inverse. An inverse means that you switch the coordinates on all of your ordered pairs in a function. The notation looks kind of like a negative power, but it's actually not a negative power. That little -1 exponent looking thing means f inverse of x. So it's not actually a power. F inverse of x. To create an inverse, we're going to do a couple different things depending on the scenario. So the first scenario that we're going to be dealing with is creating an inverse when you're given a set of ordered pairs. And when you're given a set of ordered pairs, creating an inverse is very, very easy. All you have to do is rewrite the entire set and switch the x and y coordinates to make each ordered pair kind of backwards from what it was originally. And these new backwards ordered pairs are your inverse. Switch x and y. So f inverse of x is the set. That doesn't look nice. Is the set. There we go. And we're just going to flop these. Instead of 2, 3, we have 3, 2. Instead of 4, 5, 5, 4. Instead of -2, -1, we will have -1, -2. And there you have it. There's your inverse. So that's all you have to do to create an inverse of a set of ordered pairs. For equations, we have to switch the x and y and then resolve for our new y location. So in this original function here, I don't have enough room. I'm going to come over here to the side. First of all, this is written in function notation, which means that it currently does not have a y. But if you remember from when we originally talked about functions, f of x and y mean the same thing. So I can rewrite this originally as y equals 2x minus plus 3. And then I can make the switch of the x and y. So if I switch these, I've got x equals 2y plus 3. And now I have to isolate the y in my new function. So I'm basically trying to put it back in slope-intercept form. I'm going to subtract the 3 over and make this x minus 3 equals 2y. And then divide both terms by 2 to isolate the y. So x divided by 2 becomes 1/2 x, minus 3 divided by 2 is 3/2, and there's your y. So this is my inverse, and if you like, you can write it in inverse notation. F inverse of x equals, and it's 1/2 x minus 3/2. Now, when you are trying to graph a function in its inverse, if they're lines, you're going to use the slope and y-intercept, kind of like just what we did. We had an original slope-intercept form equation. We made a second slope-intercept form equation, so we can use the slope and y-intercept for both. If it's anything else, we're going to make a table. And we can make a table for the original, and we can make a table for the new one. Now, what's nice about graphing a function and its inverse is that if you make ordered pairs for the original function, all you have to do is flip-flop all of the ordered pairs to be able to graph the inverse. So you don't have to solve for two separate tables. You can, but you don't have to, because once you get the first function's ordered pairs, inverse just means switch the x and y, so you can just flip-flop all the points. This is going to create a second graph that is reflected over the line equals x, which is a diagonal line that goes through the origin. Up like this. So we have two functions here. I'm guessing that's what this is for. And let's go ahead and graph each one of them. And I'll do them in different colors. So I'll do the original graph in purple. And it was y equals 2x plus 3. And then I'll do its inverse that we created, y equals 1/2 x minus 3/2 in orange. So my first graph starts at 3, which is here. And then to get my second point, I follow the slope, which is 2. Up 2, right 1 puts me here. And now I'm going to connect these 2 points with a nice line. There it is. And I can do the same exact thing with my second line. This one starts at -3/2, which is -1.5. I'm going to have to kind of estimate that that's right about there. And then the slope is 1/2, so up 1, right 2 is going to put me right here, still inning. If I could get this to do. There we go. There we go. There we go. All right, so let's try to connect these. Like this. There's your line. And you can kind of see that there's this imaginary line that's coming down diagonal like this. Well, that's a terrible example because it kind of veered off a little bit. There we go. This is the line y equals x, if I could draw it nicely. And you can kind of see that these things look the same on either side of it. About the same distance. Of course, it's not drawn perfectly because I'm trying to do it on this tablet, but it looks pretty good. So here's your graph and its inverse on the same coordinate plane. All right, we can do the same exact thing for this one. And this time it is a quadratic, so I'm going to make a table. For my x's in my table, I'm going to choose -2, -1, 0, 1, and 2. I will find my y coordinates, and then I will flip-flop them for the inverse. In this situation, it does not ask us what the inverse is. All it says is graph it and then graph the inverse. So I'm going to create my original ordered pairs by plugging in, and then I'll flip-flop them all to get the inverse. So we'll start with -2. We plug in -2. -2 squared is 4, plus 1 is 5. Plug in -1. -1 squared is 1, plus 1 is 2. Plug in 0. 0 squared is 0, plus 1 is 1. Plug in 1. 1 squared is 1, plus 1 is 2. And finally, plug in 2. 2 squared is 4, plus 1 is 5. And this is going to give me my ordered pairs for my original. So -2 is up at 5. This is going to be fun. And -1 is at 2. 0 is at 1. And then we've got 1 is at 2, and 2 is up here at 5. So now I'm going to just try to graph this as nicely as I can, like so, and it's a parabola. I don't like that second line. Parabola. That one's even worse. Come down from the top. That's a little bit better. So there's my original parabola. I can quickly create the inverse. All I have to do is take each one of these x's and y's and flop them over. So negative 2, 5 becomes 5, negative 2. And negative 1, 2 becomes 2, negative 1, and so on. 1, 0, 2, 1, and 5, 2. Now, plotting these points is going to be my inverse graph. So I've got 5 is at negative 2. I've got 2 is at negative 1. I've got 1, 0. Then I've got 2, 1. And 5, 2. Which is going to create another parabola, just one that's kind of like sideways here instead. And again, the reflection is coming over this line right here. So you can see this is like a nice reflection. If you folded on that line, these graphs would line up nice and neat on, well, not super nice and neat because of the way that I drew them, but they should line up nice and neat on top of each other. So there's functions and their inverse graphs. Let's talk about one-to-one functions. Now, when we talked about functions to begin with, in order for something to be a function, each value in the domain could only pair up with one value in the range. That's what the D and R mean. Each domain value gets one range value. You could not have any repeated domains. Each one had to be different and paired up with something different. Now, in a one-to-one function, the above has to be true. You still have to have each domain being different. But now we also are concerned with the range. In functions, all the ranges could be the same. You could have 1, 7, 5, 7, negative 3, 7, 24, 7. Everything could be paired up with the same range value as long as all the domains were different. In one-to-one functions, you also cannot have any repeated range values. So, no repeated domains or ranges for it to be one-to-one. Please note that if the original is not even a function at all, then there's no way that it could be one-to-one. Because in order for it to even possibly be one-to-one, it has to be a function. All right, so some important properties of these functions. There we go. If a function is one-to-one, then you automatically know its inverse is a function. It doesn't say anything about one-to-one. It just says if the original function is one-to-one, then the new inverse function is going to be a function. Second thing, the domain of a one-to-one function becomes the range of the inverse, and the range becomes the domain. That's because of the nature of inverses. You switch the x's and y's in the ordered pairs. So the original domain is now y values, and the original range is now x values, which means they kind of flip-flop sets. Last thing, any function that is only increasing or decreasing over its entire domain is one-to-one. Now, this is going to kind of come in handy whenever you see exponential functions, because on one end of an exponential function, it almost looks vertical. And so it might look like it's not a function to begin with. On the other end, it becomes almost horizontal, which might indicate to you that it is not one-to-one. Now, the nature of these types of functions is that they are always either increasing or decreasing. So in this scenario, because of this characteristic, it will be a function and it will be one-to-one, even if it doesn't necessarily look like that. Now, the way we are going to determine whether or not a graph is a function and one-to-one, we are going to use those line tests that we talked about. In the first section on functions, we use the vertical line test. Which was to determine if it was a function. The vertical line test says that you should be able to draw a vertical line anywhere on a graph, and it should only touch that graph one time. If at any point it touches the graph more than one time, it is not a function. So that's for the vertical line test. Now, very similar to the vertical line test, we have what's called the horizontal line test. And the horizontal line test checks for one-to-one. So it says almost the same thing, except now we're dealing with horizontal line instead of vertical. It says to check and see if something is one-to-one, you use the horizontal line test. The horizontal line test says that if you can draw a horizontal line anywhere on the picture and it intersects the graph only one time while you're drawing it, then the function is one-to-one. And that means that it has an inverse that's a function. So we have to check. We have a couple different examples here. The first one is already drawn for us. The second one is not drawn, so we're going to have to draw it. But we are checking now just to see if it's one-to-one. So we're only using horizontal line test. So on this picture here, I want to know if I draw a horizontal line anywhere on this graph, is it going to touch the graph more than one time while I'm drawing it? And that one's not even on there. But if you see, all these horizontal lines I'm drawing are only touching the graph once. So as long as that's the case, and there are no places where there are two touches, this is one-to-one. Now, to check the second one, we have to draw the graph. So I'm going to make a table. And in my table, I'm going to pick -2, -1, 0, 1, and 2, and plug them in. This is an absolute value function. You probably already know what an absolute value function looks like because we have talked about them. But I'll draw the picture anyway just so that we can take a look. And so we're going to plug each one of these values in, starting with -2. If I plug in -2, the absolute value of -2 is 2, and 2 minus 2 is 0. If I plug in -1, the absolute value of -1 is 1, and 1 minus 2 is -1. When you plug in 0, the absolute value of 0 is 0. So 0 minus 2 is negative 2. And then I've got 1 minus 2 again, which is negative 1. And 2 minus 2 again, which is 0. So here are my points. Negative 2 is at 0. And negative 1 is at negative 1. And 0 is at negative 2. And 1 is at negative 1. And 2 is at 0. So right here, so close to being able to do this without. Let's see if I can use this little line tool here. So here's one side of it, so close. There we go. There we go. That's pretty good. No, it's not. I'd be better off just leaving it. I'm just going to draw it myself. There's one side. Up there's the other side. Not too terribly wonderful, but you get the gist. It's a V shape. And now the question is it 1-to-1? Well, if you take a look right here's a horizontal line. It touches here and here. That's a 2-touch, which is not allowed. So this graph is not 1-to-1. Since it is not 1-to-1, its inverse would not be a function. So if they give you a picture, go straight from the picture given. If they give you an equation, you're probably going to want to draw the graph so that you can check for the horizontal line test. So let's see here. What else is in this section? Finding formulas. We actually already did this once. We found the formula for the original one where we switched the x and y and resolved. So I actually did one like this already, and you're going to see another one. So here it says inverse means switch the coordinates. We already did it. To get a formula, you're going to solve it. Now, before you even go through this madness process, you want to make sure that the original graph is 1-to-1. Because if it isn't, it's not even going to have an inverse. So you want to go ahead and at least check it visually pretty quickly and see if it's 1-to-1. Now, you probably can look at this first example here and know that it is 1-to-1, but I'll go ahead and draw the picture anyway. This is a linear graph. I need to move this down to have enough room because it starts at 8. 1, 2, 3, 4, 5, 6, 7, 8. All right, so this original graph starts up here at 8, and the slope is 5. I can't go up 5, so I'm going to go down and to the left. 1, 2, 3, 4, 5, and to the left 1. There it is, right here. And then we connect. This is a linear equation, which will pass the vertical line test. So you probably already knew that, like I said. This one is 1-to-1. So we can go ahead and find our formula. Now, the same way that we did it back at the beginning, instead of having function notation, I'm going to write the original as y equals 5x plus 8. That way, I can interchange the x and y. So I take the x and y and flip-flop them and make it x equals 5y plus 8. And then I'm going to solve this equation for y. This is a two-step process because there are two values on the same side as my y. I'm going to begin by subtracting 8 over. That gives me x minus 8 equals 5y. And then I'm going to divide both sides by 5. We get x minus 8 over 5. Or you can do 1/5 x minus 8/5. Either way, there's your inverse. This is typically how we write these types of equations, so maybe just leave it like this. F inverse of x is 1/5 x minus 8/5. And there is your inverse. In this type of function, we haven't graphed any of these. This is a rational function. You can make a table of values. I don't want to spend all the time to do that, so I'm going to come over here and go to Desmos and throw this thing in so I can show it to you. I hope I can copy and paste here, because that way it'll just make it faster for me to show it to you, and we can get to the inverse part. So y equals oh, I think I can put a parenthesis in here. I wonder if I can show you how quick and easy this is. Let me see if I pull this over here, if you can see it. Here's the Desmos application. Okay, I need to have this down here so I can see it. Okay, there's the function. So you type in y equals, and then I'm going to put this function in here. And I need the fraction bar. Let's see, where's the fraction bar at? I guess I'm just going to type it. Okay, so I'm going to put in, I already forgot what it was. 5x minus 3. And then I'll just use the slash for the dividend. There it is. Okay, 2x plus 1. And it's going to draw this picture for me. And here's the picture, and I'm going to export it so that I can copy it and paste it here. So let's export, and I'm going to copy the image and see if I can paste it right in here. Paste. Why won't it let me paste it? Well, fine then. We'll just look at it on the thing. Here. Okay. Here's the Desmos graph. And if we look at this thing and I draw these vertical or horizontal lines on here, they are not going to overlap because there is a space in between these two pieces. So we can keep going forever. And this does, in fact, pass the horizontal line test. So since it passes, that was helpful. Oh, there it is. Oh my gosh. So here it is. Here's the picture I wanted in here. Now I can actually draw all over it if I want. So we've got horizontal lines going. Even when we get down here, we're still only touching one time. So you're in good shape all the way. So this is 1-to-1, which means it does have an inverse. Now, this is going to be a little tiny bit more involved in the inverse because of the fact that it is this rational function. I still want to start by writing it as y equals 5x minus 3 over 2x plus 1. Then I need to switch the location of the x and y. And this time there is more than one x in here. So we are going to have two y's. It's going to look like x equals 5y minus 3 over 2y plus 1. Now, just like before, whenever we dealt with rational functions, when you have a denominator in an equation, you want to eliminate the denominator by multiplying all the terms in the equation by that denominator, which is going to cancel the denominator on the right and bring it over to the left. So now we've got x times 2y is 2xy, and x times 1 is x. Equal to 5y minus 3. Now we have to isolate the y. So your best bet from this point is to get everything that has a y in it on the same side, and get everything that doesn't have a y in it on the other side. So I'm going to subtract this 2xy over, and then I will add this 3 over. That way, we kind of move this stuff around a little bit. Plus 3, 5y minus 2xy. Now, the reason why I want all the terms that have the y's in them on one side is because I'm going to factor a y out so that I can get it by itself. So this is x plus 3 equals y times 5 minus 2x. Now that y is by itself, I can isolate it by doing the opposite operation here. This is multiplication. Let's divide it out. Divide both sides by 5 minus 2x. And there's your y. X plus 3 over 5 minus 2x equals f inverse. So a little bit more involved with a rational, but still same kinds of concepts. Switch the x and y and re-isolate, whatever it takes. All right. Number 3, I was going to say, I don't know why it doesn't have a coordinate plane, because I made one for the last one. Number 3 is a quadratic, but this quadratic has a restriction on it. The restriction says we want to look at the quadratic, but only where the x's are positive. So I'm going to pull this thing up again in Desmos so that we can take a look at it quickly. But if you had to draw this by hand, you would just use the table. So y equals 4x, I need a power squared, but it's plus 3. All right, so here's my quadratic, but I only want where the x's are positive or 0. So it's kind of cutting the entire left-hand side off of this graph like this. And it makes just this right arm here because we're restricting the domain. Let me see if I can export this one as well. Oh, I can even export the right image. Okay, so I want to copy. Let's see if I can remember how I just did this. Yeah, just like that. Okay. I kind of want to crop it. It's fine. All right, so since we restricted the domain to only 0 and the positives, we have cut off this matching arm that was over here, and we now only have this right arm of this graph. Restricting the domain in that way made it so that this thing would pass the vertical line test. Not the vertical, I keep saying that, the horizontal line test. Before, there was another arm over here, so if you drew a horizontal line, it would touch twice. Now, we have forced it to only be this right arm, which means that it is 1-to-1, and we can find the inverse. So, new graph, 1-to-1, yes. Let's go ahead and make our inverse. So the original function is y equals 4x squared plus 3. Let's flip-flop the x and y and make this x equals 4y squared plus 3. And now we'll re-isolate our y. I begin by subtracting the 3 over, so I have x minus 3 equals 4y squared. I will divide both sides by 4 to isolate the y squared. So x minus 3 over 4 equals y squared. And then to undo the square, I use the square root. Now, the numerator of this is an expression, which is not a perfect square, and so the square root is going to remain on the x minus 3. But the denominator is a perfect square. You can take the square root of 4 and get a regular integer, no longer under the radical. And there's your inverse. Now we're going to take this concept of domain restriction and apply it to a couple different examples here. Down here, we're going to run into scenarios where we could possibly have a situation where the original function is not one-to-one. When we do this, because we want the function to have an inverse, we are going to have to restrict the domain in order to create a scenario where it would be one-to-one and therefore have an inverse. So I'm going to use Desmos again to save some time, so we can quickly take a look at these graphs. So the first one is y equals x minus 2 cubed. I need a cubed. And then there's something with it though, minus 1. And let me move this back over so we can kind of see the whole thing again. And let's export it. So here's my picture for this first one. Whoa, this is going to be too big, so let me just make it smaller and see if I can move it up to where it belongs. See if I can throw it in here. Nope, it's fine. Okay, so we're going to look at this guy first. This is the first one. I don't know why it won't let me put it in the picture. Again, this is the one that has the cube in it. And if you take a look at this one, I think it was supposed to have a square in it. But this one, if you look at it, passes the horizontal line test. So this one originally is already one-to-one. And if it's already one-to-one, then it does have an inverse. So I don't know why I scrolled all the way up. Yes, one-to-one has inverse. Because in order for it to have an inverse, it has to be one-to-one. And if it passes the horizontal line test, then it's going to have an inverse. So that one's not really helpful. Let's look at the second one, which is an absolute value function. And so in a similar fashion, we're going to quickly graph this thing. And Desmos will graph an absolute value. Where is the absolute value thing? Right here. Absolute value, x minus 12. And let's scooch it over because here it is right here. And you can kind of see already that we're going to have an issue with this picture. What on earth? All right, let's get rid of these lines. Okay, here's my picture. Again, I don't know why it won't go up in the thing. But if you look at this thing, right here, in an absolute value, you're going to fail the horizontal line test in lots of different places. So what we need to do when you have this situation, we need to split the graph down the middle so that there is no, and I would love it if I could draw a straight line on this thing. Split the graph down the middle. The thing is not cooperating with me right now. Copy. There it is. Let me erase this again. Okay, so we've just talked about how it overlaps. Now maybe I can use this thing. Okay, let's split this graph down the middle right here. There we go. So if you cut this graph in half and kind of remove one side or the other, now removing this whole side of it and kind of pretending like it's not there, starting at 12 and going on to the right, you won't have any repeats because you're just right here now. In a similar fashion, you could go off towards the negatives. It doesn't really matter which way you go, but you want to cut one side of the graph off where the repeating is happening. So I can restrict the domain in this case, since it's not one-to-one to begin with. We can restrict it to x's that are greater than or equal to 12 only. That goes from 12 on, which will give you the right vertical arm like that. Or you could go with x's that are less than or equal to 12 only, which would give you the left vertical arm. But regardless, there's no repeating happening on left and right. So either one of these is going to be fine. But again, we're cutting the graph in half vertically, removing the matching arm on the other side. And that's how you will restrict domain if you have to. So that is it for inverses. And that is the last section in Unit 4. All of the videos for Unit 5 are posted, I think with the exception of one of them. But those things are already up and ready to go for you. And I'll get that last one done probably tomorrow or Thursday. And you'll have everything for the rest of the semester ready. So I hope you enjoyed, and I hope this was helpful. And I hope you liked the Desmos graphs. I recommend using Desmos if you want to look at something pretty quickly, because it just makes it a little bit easier to look at. And those graphs are nice and perfect because the computer draws them. So let me know if you have any questions, and be on the lookout for those other videos. Take care.